Hello, my name is Dominic, and I want to talk to you today about the inverse square law. What exactly is the inverse square law? Well, it's a pretty fundamental principle in physics that has to do with how measuring radiation depends on your distance from the source of radiation. Well, first things first, we have to understand how radiation sources work. Now, any source is going to emit radiation in all directions equally. Omnidirectionally is another way to say it. So, we can think of that a little bit like the area of a sphere. And in fact, we're going to use that in our formula here. So, any measured radiation intensity that's separated by any distance from a radiation source is going to be equivalent to the amount of energy emitted at the source divided by 4 pi r squared. So what's changing our intensity here from the source? It's our distance of separation, or r, our radius in here. So from a radiation source at a radius of r, so essentially 0, your intensity is going to be equal to your source. If you double your radius, though, it's actually going to be 1/4 of your original source. And if you triple your radius, it's going to be 1/9 of the original source, 1/9 the intensity. Now, can this translate to real-life experiments? We're going to see today. So here I have a sample of natural uranium ore in a Geiger counter. Don't be alarmed. I'm actually safer standing next to this than I am in a car on the highway. So, we're going to take an average count per minute, of this radiation source to start off with a radius of 0, and then we're going to move up. And we're going to log it on this graph here and see if it actually is inversely proportional to the distance squared. Let's see how that goes. Okay, so we've obtained our source radiation value. Our average count is about 255 counts per minute. Now, it's going to fluctuate, but that's our average after about 1 minute. We're going to set that as our Y value maximum. We're also going to set our Y value minimum on this graph to 25 CPM, and the reason for that is background radiation. There's never going to be a 0 CPM count if you're on Earth. There's external forces that contribute to background radiation levels. I'm going to save you the pain of having me graph out every single 5 centimeter distance of separation from our source, but I'll show you a few more as well as our final distance of separation on this ruler here. Okay, so we've just graphed 5 centimeters of separation. Now our calculated expected intensity is about 81 counts per minute, but in actuality our average was found to be about 96 counts per minute. So we've graphed that. Let's move on to a few more points. Okay, so I've graphed the remainder of the points, and we can see that this appears to be an inversely proportional graph from our distance to our intensity of radiation. Now, from 5 centimeters we get a counts per minute of about 96. So it's not perfectly 1-to-1 with what we mathematically expect, but it's about right. Now, keep in mind the values at around 30 centimeters from our source radiation sit around 32, for example, at 25 centimeters, to 28 at 30 centimeters. So you have to keep in mind that you have to subtract our background radiation from those values to get the number of particle interactions with the detector per minute. So it's actually quite low. But you can see here just the dramatic drop-off in intensity from distance of the source. So yes, what we saw here in our experiment shows that radiation follows the inverse square law. Now, it's not perfect. There is some experimental error, and real life isn't a 1-to-1 representation of math, but it's pretty close. Okay, folks. Well, that's all today for the inverse square law. Again, my name's Dominic. Thanks for watching.